Good evening, good morning, or good afternoon, everyone. As Professor Liu said, wherever you are. And I would like to thank organizing committee for inviting me and sharing some of our research that we have been doing at Hong Kong Polytechnic University relating to contactless palm print identification. So to get started, I will talk a little bit about the historical aspects of the palm print identification. Palm print identification is actually not new. And as per as the references I cite here or known to me, China was the first known culture to use the fictional rich impressions for identification. And the records indicate it started long back during the regime of Qing dynasty. But in Bengal, in India, in 1858, uh, it is best documented first modern practical use of full hand impression for personal identification. And this person, Rajdar Konai, his ink impressions are documented by this British civil servant in the province of Bengal in India. And it was a building contract that he asked him to put his ink and provide impression for the contract. And that began a formal systematic process of using contact-based palm print in India. Now, palm print impressions have long established their uniqueness, identity, and a reproducible claim of identity before the current systems using a contactless pattern. So the images does show there how typically the palm print patterns were acquired using ink pad and later on using contact based scanners, as you see here. So the question comes, why palm print? There are many other possible modalities. So multiple reasons for doing a research and development on palm print identification. First is a failure of fingerprint, which is a widely used biometric. But NIST studies as well as the studies from UIDAI indicates that typically around 3% of the population may not have a usable fingerprint, and it makes sense for alternative modalities. Next important reason is multimodal biometrics. More than one pieces of evidence can significantly enhance the security. Mobile security, fintech applications, convenience, and also in the medicine, it is shown from early research that some palm print lines have a correlation with heart diseases. And also public security and surveillance. So, multiple reasons for pursuing research on palm print identification or particularly contactless aspects here. Some of these images that I show here that indicate for public security application how the palm print identification can be useful. To let me go back a little bit on earlier research or the first paper that we published in 2003 on PEG-free contactless palm print identification. So right from that time, 20 plus years of research, development, and progress, you see the timeline to move a basic concept into a real world application or a system. And it has been possible with the help of the research, which has moved now from traditional methods to deep neural network based methods, academia contributing a range of data sets, benchmark, and industry providing solution in terms of sensing and actual deployment, and more importantly, driven by the law enforcement application for mobile and forensic investigation pathways. So it takes a significant amount of time, you see, from a concept to moving into the real world deployment. And this was the probably the first paper in my knowledge for completely contactless or a pack-free identification. Now, looking into the market, current market for the palm print payment, and we can see the applications, especially in mainland China, widely used for e-payment for the fintech. So I got these numbers to indicate that in next 5 to 10 years, it is expected to have a significant amount of growth for palm print identification, approximately 10 times revenue expansion over the decade. So currently, the numbers you see from 2024 from 68.4 million to becoming closer to 10 times in 10-year projections. And that indicate significant potential in this modality for largely the fintech segment. Although there are other application also like retail or a general purpose security or access control applications. Now the question comes, what are the challenges now? What are the deployment challenges? What are the challenges for the next phase of the research? So I want to go through them briefly. The first challenge for the popularization of contactless palm print identification is the cost of hardware. And you can see some of the images that I use it here to show the deployment of palm print, contactless palm print in China as well as in US, Amazon One images here. And all of these show the need for a specialized hardware. And this is one reason that could slow the mass adoption of contactless palm print identification. So this remains the first challenge for popularization of palm print identification technologies in next 10 years. Now, the second challenge is relating to the public acceptance and privacy. What does it mean? It means that, as with all the biometrics, users have a valid concern about how and where their unique biometric characteristics, templates will be shared and protected. And currently, if you try to search and find distribution, as if these numbers are to believe, it's roughly 50-50%, 50% about on the cloud and 50% is storage on device or in premise. The next challenge is integration and complexity. Integrating new hardware and software into the existing financial infrastructure like ATM networks or point-to-point sales, it will require a significant amount of investment and the effort. So that remains the next challenge. And that will lead me to focus on the first challenge, that's the cost of hardware. And I've seen a good amount of research and development efforts, particularly from the industry, on adopting this and how they can make it ubiquitous. That is, alleviate the need for the specialized hardware. So I'm going to focus my talk on this aspect, that how we can develop a completely contactless palm print identification using a general purpose mobile phones, ubiquitous. If you have an app for fintech and other application, I think that can promote a mass adoption of palm print biometric. So the first step, obviously, in any biometric identification is the detection. So when you're using a smartphone or mobile phone, the question comes how to detect your region of interest or the palm. And number of ideas we have like object detectors, YOLO, and so on, that can be a very good candidate. Very fast, very accurate. Nowadays, it's shown to work very well. Now, the palm print identification is a little specialized problem, and one may need to think: is it really we need to use the popular object detectors for identification of region of interest? What is the best possible way is to use a key point detector. You essentially need these two key points, as I shown here. They are shown four, but typically we need these 2 points. You can draw a straight line, and from the center you can extract a fixed ROI region. You do not need to have a more complex solution like object detectors. So a simple network like a unit, as I shown here, could suffice. A properly trained network could give you a sufficient or accurate performance for detecting ROI, particularly critical for smartphone-based application. So this is something that we attempted that, and I tried to show some results from here, and it's found to be very effective. What I was showing just now was accuracy, mean key point distance, but more important is what is the model size. It is about number of parameters. Is less than one tenth of the fastest YOLO model there. And also, whenever you see the accuracy is also key point is of significant interest. So these results from the red plot, I'll not go in detail, also indicate that on publicly available data set, you can also get relatively better accuracy as compared to the other kind of object detectors. Some of the images here I bought to show you the same approach, the result from the same key point based approach, showing these out of plane images. And you can see the detection is quite satisfactory and it works quite good. Now, one of the popular solution you see recently in the literature is to use MediaPipe. MediaPipe can provide you 20 something key points from your hand, and that can allow you very quickly extract ROI. And that's also one of the efficient approach. But the question is, as compared to detecting only key points. Now, one of the challenge from the media pipe based contactless detection is that you need to have all the key points available. And when the region, all the key points are not available in the image frame, that detection often fails. So I give you an example from Cassia. This is a publicly available data set from Cassia, and you can see you try to detect ROI using media pipe based approach. You can see it's not successful. But if you use the key point based approach using a simple unit, as I shown you, you can detect it quite accurately. So a number of advantages for pursuing a key point based approach for detecting contactless ROI from the smartphone based platforms. Now, the next step is importantly to detect presentation attacks, and like reply attack, or it could be a print attack, and so on. A number of solutions are possible here. I bring some of these images, and these solutions are quite popularly used. Very similar solution for face recognition, and like optical flow, you can ask the person to put his palm in a particular region, or more effectively is to ask him randomly to show one finger or two finger or three finger. For an example, this frame he shows two finger, and you can say it can detect a real, or you can ask to show the randomly three or four fingers simultaneously, or close the thumb. So this is one of the solution that we developed, and it works quite effectively. There are also other alternatives like RPG signal. And it has been very popular for face detecting liveness, and that can also be a candidate. And I wanted to show you some of these signals samples for the real versus a fake. But the problem with the RPG we notice is that you need sufficient time, typically 3 to 4 seconds, to generate this signal, reliable signal. And also the distance with the mobile phone need to be controlled. That could be not so convenient, but it depends on the security level choice. One could also choose this. Uh, Once the presentation aspect has been handled, important part also is to detect whether there is a blur in the detected ROI. And the number of methods can be used to detect a quality of ROI region. Typically, some of the edge detectors and manipulating the gradient within small blocks and their average can give you a sufficient quality measure to reject. or accept ROI to move it towards authentication. And some of these results on the right hand, if you see 0.83 versus zero point 0.5, this is a blur image. And this from publicly available data set. I think this one is IDD. In this context, I also want to share some solution that we developed for contactless palm print identification. It's an Android-based solution. It's freely available if you would like to try. So I take this opportunity to share a QR code. It can provide you multiple levels of security and also follow all the typical guidelines for the implementation, for the usage. General public typically like encryption of the template, security check for the mobile tampering to enhance the database and the backend security. This app will also incorporate the need for a token from the Google Play, and the algorithm is also well protected, and it's a quite impressive. So if you like to try, yeah, I take this opportunity to invite you to use this QR code and try. But it's only limitation at this stages. It's only for the Android platform. Okay, with the widespread use of LLM in the research, I was also tempted to find or explore what LLM says. If, as a naive researcher, I'm looking for a very good algorithm from years of research available on the net. So I gave this prompt. I wish to use an algorithm for large-scale contactless palm matching. Can you suggest one or two best algorithms that I can use to achieve highest level of performance? And you can see the output here. And it provides you some solution. And these solutions typically you see, for an example, uh, CNN, ArcFace based. These are typical solutions, work very quite well at some point of time for face recognition, but they can give you some performance, but not or anywhere near to the state of the art method. So here, my search, I was using Gemini here. I don't think it's useful. So in that context, so next I gave a same prompt to DeepSeek, and it makes sense for me working in Hong Kong. I can use DeepSeek very well, and I do use it. And then give a same prompt. Also, from mainland, there are a significant amount of research in contactless palm print is from China only. So it makes sense. Maybe this model has learned something better. And I gave the same prompt, and I'm looking for the solution. And this was the output that I shared with you on a screenshot. And it suggests to use a coding method like, as you can see, it is suggesting to use competitive code and a Gabor-based filter solution. I would say it is better as compared to Gemini, but quite outdated. And why quite outdated? I would like to explain this. In 2017, we have presented a statistical matching model which is applicable to all these kind of codes like COM code, ordinal code, RLOC, and so on, to show that using a binary feature representation, one thing, and secondly, by using a one-to-one matching strategy, can provide you the most effective and efficient solution for contactless or in general, not only for contactless or contact-based palm print identification. So in that work, we put all these kind of codes, very popular at that point of time, into a framework, and in an attempt to ascertain statistical modeling of the score distribution. So very briefly, I try to explain that how do we model the distributions. So let us first characterize the inter-class matching attempts for the two subjects that they are completely unknown. So such matching events are eventually or effectively random events. That is, the likelihood of these codes, palm code or com code, they match or they will not match is equal. And that's very important assumption in any of the two codes that you are trying to match. So it can we can reasonably assume that the distribution of this interclass imposter match score, it will follow binomial distribution. And we also have a theoretical support from similar distribution pursued by the dogman using millions of iris code matching. So following that binomial distribution, as you see here, where the P is the success probability, and the second variable here represents the number of modeling attempts or a trial. That also can depend on the size of your template or size of feature matrix. And so we can model this as a binomial distribution. And we always know that any well-designed feature extraction method is expected to generate the code, whether it's a COM code or ordinal code, there is an equally likelihood of palm print features available for all possible aspects of these code or different possibilities of code. So the probability that each of these encoded results in the template would be 1 by lambda, where lambda are different possibilities. To a layman language, we know that there are orientations, so different kind of orientation, whether you choose a 2 or 6. And similarly, we can also model the intra-class match score. And this modeling will show the best separation between genuine and imposter or interclass and intraclass can be achieved only when lambda is 2 or the number of orientations are 2. And this theoretical assumption is also experimentally validated. So in summary, let me try to put it in a simple language. It's like this. Previous work did consider to enhance number of encodings or number of orientations, but the probability of falsely matching the imposters will also increase, and that factor possibly was missed. And this was corrected here to show that lambda is equal to 2 or the number of codes equal to 2 can give you maximal possible separation. It effectively means not just the accuracy, but also the template size can be significantly reduced. So I'll not go into detail on the experimental result, but just to show that this reference also shows a reproducible experimental result to validate that idea. So simply you can see the template size is significantly reduced, and also the matching time and also the performance noticeable. So these are results from different publicly available data sets, ITD, CASIA, and these codes are publicly available if somebody would like to try. So yeah, the research has moved far beyond the initial work on the palm code or COM code or so on. So that was the one thing that I want to share. Now, coming back on the palm print identification, particularly contactless, just like fingerprint, researchers are now looking for some very strong baseline that they can be confident that if they are doing a research and their performance is better, then they have made a case or success or break. So it's very difficult. I receive a lot of queries regarding that. What can be a very strong baseline which is reproducible, I could use it. This answer typically is available, I believe, in the fingerprint domain. If you have a commercial fingerprint matcher, they really perform very good. If you don't have, you can use some matchers in a trial version, like you have a Verifinger for an example. What about palm print? So palm print here, I'm sharing you one of the very strong baseline. If you try yourself for contactless palm print matching, it's available freely here. Again, it's a trial version for 2 weeks. But if you try this, and you will possibly find out that it gives you better performance than many of the papers that I have looked at in last 2 years, including those in transformers. And this particular matcher also can provide you the detection. So it means you have option. You can input the whole the image uh, uh, and let it segment itself and give you the match score. That's a confusion matrix. Or if you have ROI segmented by some method you think is the best, you could also use just ROI to generate matching accuracy. So it's a trial version. It's also available on the Linux platform, and it can be used as a baseline method for performance evaluation. And for that reason, I just share the code that if you like, if you have interest, you could download it. And yes, it's also protected by already issued or granted US patent. Now, I wanted to move on talking about real world contactless palm challenges. That some of these problems that I had time to work in last decade. One is relating to the long interval. We always have a question, and like other biometric fees, this is well studied that whether the palm print changes its pattern with the aging and so on. So I happen to collect a data set with 15 plus years of interval. And these are some of the images. On the first row, what you see is a 15 plus year before, and next row is the same hand, same palm after 15 plus years. And obviously, you could find out there are more creases on the second row as compared to the first one. So, presence of extra creases with the aging is the reason. But what about the accuracy? How does it match? So one thing is, as it can be observed, that this data set is publicly available also, that these major palm print lines, they remain fairly stable. So I happen to pursue this using a spectral domain approach, which at that point of time was the best possible solution for matching contactless or in general contact based also the palm print images or using publicly data set. So here you can see the image pair I show, their match score is well below the decision threshold. Here means towards zero is the better, and then they all can match successfully. So it turns out that some of the effective methods they still can match long interval palm print images. Uh, but not all. So this data set I happen to collect in Polio, as well as majority of that was collected in India in some village, and these are the images that shows the real world challenges. And you can see general public tend to write things on their palm, writing the telephone number, mobile number. Some may not have even 5 fingers or more than 5 fingers. And more important challenge is the last row, if you see. This is popular typically in regions like India, also Pakistan or neighboring countries. That is use of these mehendis or these artistic patterns. So some of these images that I show you here from that data set. And this is an image of a person uh, heavily engaged in the manual job. So you can see some of his creases have become flat. And this is an example of having these artistic patterns. And that makes it really challenging. If you try to match before this pattern and after this pattern, it doesn't match. The performance is really very poor. So this is score here. These are failure cases, non-matched image samples. And then you see the receiver operating characteristic using the SOTA method or whatever you develop new on. It's the performance is horribly low. So there is a need for further research that how we can use these real world images to achieve an accuracy which is acceptable for real world applications or the deployment. Yeah, this data set is in public domain. Another related topic that I thought I will share with you is regarding classification. You don't see any work so far in my knowledge on contactless palm print classification. Then the question comes, is it needed? Why it is needed? or will it be useful? So those answers all we can learn from fingerprint classification, that why it is needed or how it is helpful. So those all arguments I think will apply for palm print classification also. If it is possible for us to do a classification of palm print images, I think it can tremendously help us, not just to enhance the matching time, but also to accuracy. So the palm print images can be classified into five categories based on these major three popular lines. And nowadays, the attempt is always to look for codecs or elsewhere LLM to ask, can you do this job? So one of the MSc student working with me, he attempted to try this codex Chat 5.5, and in an attempt to extract these line, and you can see the accuracy is not so good. He further pursued this for this phenotype classification, yeah, but no, it was not an acceptable accuracy. Finally, we were able to get some results by using a series of classifier one after another, firstly classifying into two big categories and narrowing and so on. So here the confusion matrix shows the accuracy is not very high, but it's first step is quite good. Over 90% if you see confusion matrix, the diagonal numbers if you see, and off diagonal shows the error here. And for just the sake of curiosity, because all these experiments were done using publicly available data set, and then you can see the distribution of different phenotype classes in these data sets, notably Indian data set ITD, 21 largest number in Sydney, and so on. So this is a new area that not no work has been done, and one of the MSc student is working with me and recently submitting some output for a conference publication, possibly, or a journal. Now, another problem is a cross-spectral matching palm print images, just like for iris or face, from two different spectrum. And there also, this area also has not attracted noticeable attention. And there are multiple use of this problem for matching cross-spectral palm print images. So this line I pursued quite some time ago, that you can try make an attempt, because there are publicly available data sets with which will provide you both the spectrum. It's also from Polio and also from Cassia. So I pursued a very popular approach, a spatial domain approach for using these binary masks to encode the feature, because they can provide you very efficient encoding and also matching using a Hamming distance. And the approach was largely predominantly focused on extracting microstructure or micro patterns in two matched images. If you visually see from your eye, you try to match these gray level connections, forming a kind of patterns in two set of matched images. So I pursued extraction of these microstructures from the dictionary, and the dictionary can be found, but all of these micro patterns may not be useful for all the biometric. So there is a need for the selection of the micro patterns which will represent or encode microstructures for encoding discriminant features. So the slides, the images here shows these kind of possible microstructures using encoded from the respective mask, and there has to be a selection of from the possible combinations available. You can call it as a dictionary for a particular biometric to pursue here. The problem is the cross-spectral palm print identification. So during the training phase, you can choose a selection of a different mask and the respective weights, largely to achieve a best separation of interclass and intraclass match score. And so I'll just in the interest of time, I'll not go into the details of these optimization, which is a typical process. But I'll share with you some good results that it has using a publicly available data set. This is a Cassia multispectral, and you can see what is the baseline method. There is a very interesting work on the selection of multi-lobe ordinal filters using a multi-scale and also multi-orientation. The filters, ordinal filters, from there you can make a similar selection and also the weight. So I think that's a very strong baseline that I use to show the efficiency and effectiveness of these microstructural pattern extraction that I pursued. And the blue line on the top shows the performance from this approach. And it's a significant improvement. And that comes on the top of efficiency because the binary mask extraction, as compared to Gabor filter based or ordinal based, which are gray level operators, can save you a significant amount of time. So this image shows what you're trying to match, left with right, a palm print with palm in images. So this is another publicly available data set, polio multispectral data set, on which the performance is shown near perfect. The red plot shows there. It's not zero ER, but near zero ER I can show you. And using what is the training set here and what is the test set. And yeah, this approach using micro pattern exemplars to encode microstructures into biometric images is quite efficient, quite effective. And also the code for this approach is publicly available, and I share the QR code also. I think it appears on my website. Another aspect, the problem which has not been pursued sufficiently, or nil almost, I should say, is matching a left palm with the right palm. So while working in this area, I found a significant amount of similarity for majority, if not all, of the data set I see between left palm and the right palm. These are images that I bought from publicly available ITD dataset and also for other dataset, which I could mark myself to underline. And this. So we pursued this whether it's possible to match left with right, registering from one end and matching from another, and so on. Also, many real world applications. And this is the first attempt, curious attempt we did a long time back to find the similarity between left and right. Please note that such similarity has been documented in the medical literature, and that forms a good basis for pursuing this idea. It's in yeah. So if you read the paper, proper citation, you would be able to find. So using a very simple neural network with a fully connected output layer, this attempt was made after particular network training to use a polio data set to see how you could match. And you can see the accuracy is reasonable, quite good. Actually, what you're trying to match is a very different problem. Trying to say that there is a good similarity, and that was a point. And that brings me to the point. I see many people combining left and right. It's always important to present experimental result separately. Given this paper or a reference, it has not been noticed, so I thought I will include it. Now I am just also looking at the time, so this can be the last slide, very important one. What does it makes to make a system which is explainable? For particularly the law enforcement is looking for explainable solution. They don't follow the math score is not sufficient for them. So an explainable alternative for palm print matching, obviously what is expected, it should also provide highest level of accuracy, is pursued recently by us. So these are the ROI images, and you see a small dot. So these are key points. So we train a network to identify key points from the any unknown given palm print images. So once a key point has been detected by the trained network, next step is to find the feature vector that will encode the interpixel relationship in the neighboring region. So you get a key point as well as their respective feature vectors from the first two matched palm print images, you have a key point location, spatial location, and also the feature vectors. The next step is to find what feature vectors are corresponded. Everything may not be corresponded. That may be same person. Correspondence should be expected to be higher. So a correspondence network need to be trained. And when it is for the deployment, for the testing, these key point locations or feature vectors which have corresponded, which has already corresponded, has to be identified. And using those only those corresponded feature points, having scored above certain limit, you can build a graph, two separate graphs for two matched palm print images. So this graph, you can see visually, they look very similar. Left and right, they're very similar because they are from the same person matched. And of course, you can generate a match score also using a trained graph neural network that can give you a match score. And so this approach can be explainable. And also one could pursue the uniqueness of these key points. Remember, these key point locations are marked based on the major palm lines and assuming it's a piecewise linear approximation of the curve. So you can always have these dots located along these curves. So this is one of the important direction or the approach to achieve explainable contactless palm print identification. And before I close or we go for Q&A, very quickly I wanted to go for the best practices in the performance evaluation. So the best practices, if you would like to follow for performance evaluation, if it is a deep neural network, always present cross database, more importantly, the cross sensor and cross session. Cross database is very common in deep neural network. Cross sensor, cross session, and then you can see the current sort of method where they perform. You would like to see a great room for or the need for improving the performance. Evaluation typically using ROC is a very critical and always use mask, not matching the whole hand, whether you're matching a hand or you're making a ROI, palm print ROI. It's a two session standard protocols you have. Single session, always pursue for all possible combinations of genuine or imposter. Also use a very strong baseline, which is publicly accessible. One baseline I provided, or even the better one, if you know. And then always present a template size and the complexity for the method. And finally, I would like to acknowledge my collaborators, number of names here, Yang Liu, who was undergraduate student, and so on. Ray Chan Kunwai, yeah, he's the mind or brain behind the app that I share, the QR code. And the next one is a MSc student pursuing his project, and so on. And these are some of the references. So I just want to make sure we have sufficient time for Q&A. Thank you.
Thank you so much, Professor Kumar, for such an insightful talk. Now, let's move on to the QA session. And we have received some questions in the Q&A panel, so let me go through a few of them. The first question is, most recent research focuses on improving recognition accuracy. So, do you believe that secure template protection, for example, cancelable biometrics, homomorphic encryption, or deep hashing, should now receive equal attention?
Oh, yes. This is a point I also wanted to underline. Didn't have time. Yeah. So using this approach, I don't see any good attempt for face recognition. There is a good amount of recent work. If you see, some of the top conferences have pursued this, matching the templates in an encrypted domain. So this is one good direction to pursue, and there is a real need. The solution I used for a mobile app that I was talking about, templates are encrypted, AES encryption we use, but matching them in an encrypted domain and generally known to decrease the performance. But that is what is expected, and there is a good amount of research in the face. So yeah, my answer is yes, I'm positive, and this is one direction that the students or whosoever want to pursue the research to go for. Yeah.
Okay, and thank you. And the second question is, So the methods show approximately like 99% accuracy on the public dataset. Does this suggest that the RGB imaging has reached its practical limit and making NRI or multispectral imaging essential for future improvements?
No, actually, this is a very important point mentioned, actually, that people show a 99% accuracy. Now, it is true for some of the data set. For an example, Tonji Palmprint data set. In 2017, also, the paper which I use it show, 0% separation between genuine and imposter using two-session standard measure because that's a two-session data set. So already achieved, you can see 100% or 0% ER or complete separation of genuine and imposter. But people still pursue until now, actually, to find the performance at 99 and so on. So you ignore the literature. Second thing is, I tell you, when you see the 99% accuracy, always ask your question, what are the match protocols used? Did the authors have used all the genuine and all imposter combination? Whether it is a cross data set, cross session, for an example, then you see there is a significant room for performance improvement. So I don't think that we have significantly improved the accuracy, considered 6 degrees of freedom in the completely contactless environment. ROI detection with the help of deep network has significantly helped us to reduce that domain gap. But still, there is a big need for when you change the scale and change the distance, and then a real world environment, out of plane. And no research has been done actually. So I think there is a significant room here. Whenever you see a very high performance, please do ask these questions, which I pose it. If you look for any publicly available, I think Xi'an Jiaotong University also got a good data set with their multiple sensors. And when you try to compute this cross sensor, then the performance is not so high.
Okay. And there's another question. Since contactless systems do not physically touch the hand, it seems harder to perform liveness detection compared to those contact-based systems. So how should we approach the anti-spoofing for contactless thumbprint?
Yeah, this is a very good question, and I try to give some answer to there, and it's a big challenge also. That's the reason that major solution in mainland they are using NIR to get more confidence, also liveness, and also take benefit from the palm being patterns. Now, liveness detection is a very critical, and there are a number of approaches. Like in the app I shared, if you want to try, you can ask the person to do a randomly present the hand, open or close, or randomly present the fingers, or so on. You can also uh, the number of solution work well, but definitely the bottom line is the inconvenience. How much inconvenience you could have it, but that can justify the application if it is just unlocking or access control in an office environment or attendance, that could work very well. Or so anti-spoofing, one of the direction that I think yet to be pursued. We did some work is 3D. Success of face recognition tells us that it was largely 3D that achieved not only a good accuracy but also very strong anti-spoofing capabilities. So something that can also be pursued. And the model now does allow you to get a 3D from a single 2D image. We have pursued it for fingerprint, and that can also be pursued for the palm print. So I fully agree. The anti-spoofing is the challenges, but there is almost no research in this direction. So some of these solutions I talked about, they need to be evaluated and see which method or combination of these methods can provide you a sufficient level of security for intended applications here.
Okay. And I see here a lot of questions are about the same topic, and I will choose one of them to as a representative. So the question is, I guess the contactless palm images can look very differently depending on the device, lighting conditions, and hand poses. So when moving from the control settings to real-world scenarios, what do you see as the biggest bottleneck for maintaining the recognition accuracy?
Yeah, this is what you mentioned actually already. Now, I think this question answers the previous question also, the challenges for contactless palm print identification. Real world identification is really very challenging. Now, from my point of view, what are the real challenges? First is the normalization. Always one have to pursue the best way to detect and localize ROI, and that is with respect to not just the scale changes, but also the out of plane. The images may not be out of plane because the solution which I am presenting or I shared with you for a mobile phone, actually that will ask you. So you move your hand up, lower, just like for we can borrow the ideas from the face recognition application. They will ask you to open your eyes or go to a particular ROI location to expect some degree of cooperation. So, but if that is not the case, like for public security application and so on, so a lot of the methods available in computer vision domain can be incorporated and tried. That is, whenever it's out of plane or tilted, how that can be corrected, and to estimate, and then including estimation of 3D estimation of 3D from these real world images to provide the cues for the correction. So the first step is to meeting the challenges on the ROI normalization is very important. And here, a lot of, always what happens is in any application where for palm print, nobody presents ROI, they all present your hand, full hand. So, and then how can we utilize other parts to get into but the reliable part is this, given the level of imaging resolution we typically use. So can we use that actually like MediaPipe does it? MediaPipe uses all these key points to get a very accurate ROI location. But once these points are not there, it's not, it's very challenging. So the question itself is very challenging that ask for. So I think it just we can learn from the experiences in the face recognition domain that handling the localization, alignment of the region of interest from these real world challenging images. If it is like painted or written, script is written, mobile phone number is written on somebody's palm, how we can remove it? I think it should be possible. We could use the de-running models and so on, but people have not pursued that. And so, step by step elimination or a correction towards generating a more reliable ROI and a properly trained deep network can possibly give us a good solution.
Okay, thank you. And here comes a new question. Has authentication with partial thumbprints has been explored?
Yeah, I did see some conference papers by randomly blocking some of the ROI regions to achieve that. But I have not seen more than that. I think one or two conference paper long back because there was a good research for these occluded face recognition to and incorporate the same idea for palm, but you don't have that data set, so you can randomly put circles, rectangles, or squares in the images and see where is your matching accuracy. So some is initial work, but not using a database which is really occluded. Like it exists for face. Face, there are some database where you can see large number of images are occluded. Yeah.
Okay. Well, here are too many questions. Here's a new one. Since capture device like smartphones affects the visibility of primary and secondary lines in contactless palmprint, are there any research or suggestions would help to overcome the matching limitations due to varying levels of details in ROI image?
Yeah, I think this is a very good, insightful question. If I understood right, it's asking that various levels of features exist in contactless palm print images, varying resolution, because there is also 6 degree of freedom, so there are scale changes. And sometimes you may see more feature depending upon the illumination setting, distance, and so on. So if I understood the question is that can these different level of features available, is there a study or can they both be used? Certainly, this argument will also apply for other biometric also, including fingerprint or the face. So same thing can be said it here. But once a real world system is designed, then it's designed for some intended minimum resolution, particularly smartphone based. So you expect some level of because if one or two images available in a better shape or resolution, you don't extract the features for that. You just scale down that images for the deep network has been designed. The depth of that network has been chosen or trained. If it is a transformer, transformer. We don't have so many images to make a good training for transformer. I've seen some of the papers, but if you match them with a conventional method, they don't give you very matching accuracy, I should say. I've tried recently. So certainly there is a room for finding different kind of features available from contactless palm print images. But to see the effectiveness of any scheme on such kind of images, a large data set has to be collected. Baseline methods which to work very well for a low resolution should be tried, and then only the gap can be found so that you explore new possible features to improve the performance. Yeah, that's what my understanding is. Yeah.
Okay. So due to the limited time, I think this will be the final question. The question is, did the explainability analysis found that existing method being biased to particular ridge structures?
So the question is the explainability analysis found that particular bias for the ridge structure, is it?
Yes?
Yeah, this question actually is not clear to me. Now, what I presented was a very brief snapshot of something that is yet to come out in public domain, just for illuminating. Now, but you can borrow the ideas from published paper. CVPR 2025, we have a paper on similar ideas, actually, explainability. You may want to look at that. So explainability, one thing is generally explainable without the use of computer, what is matched, what is not matched. It also includes the concept what is matched or non-matched, what is the probability of false random correspondences. So you have to prove these statistical observations are widely used in the law enforcement. Whatever feature I am talking about, whether they are key points for the lines, how much, what is the probability they can be matched in randomly matched or imposter persons, and what is the likelihood that they cannot be matched. So that data combined with what I was talking about is comes to be the full explainability or that is expected from law enforcement. So I only showed one part of explainability. I didn't argue about the others. That needs a database distribution of these features to show what is the probability or likelihood they will randomly match between two matched palm print images.
Okay, thank you. I can see there are still many great questions coming in, but unfortunately, we're about to running out of time. Thank you so much, Professor Kumar, for the wonderful talk and for answering all these questions. And thank you for anyone just for joining us today. The recording of this webinar will be reviewed and uploaded to our YouTube channel. So feel free to revisit it at any time. And please stay tuned for future webinars in this series. And have a great day. And that will be all for today's webinar. See you next time. And thank you again, Professor Kumar, for joining us today.